Picture this. You're looking at a thriving, bustling population of adult turtles in a wetland. It looks great, right? Well, what if what you're actually seeing is a population on the brink of total collapse? Welcome to this explainer. We're talking about a terrifying phenomenon known as the demographic illusion. See, because turtles have such incredibly long lifespans, those surviving adults can completely mask the grim reality that absolutely no new turtles are surviving to replace them. By the time you actually notice the adult disappearing, it's already way too late. So, let's dive into this. Today, we're exploring a critical early warning solution called TurtleStatus. Essentially, this is a powerful, browser-based screening framework, and it's designed specifically to assess these turtle replacement pipelines. It basically gives conservationists the crucial lead time they need to actually do something about it.
Here is our quick roadmap for today. We've got 6 parts: the demographic illusion, the replacement ratio benchmark, preparing observation data, the 4-step workflow, interpreting linked evidence, and finally, essential limitations and scope. We'll start with a bit of background theory before moving right into a highly practical, step-by-step user guide for the software.
Starting with Section 1, the demographic illusion, and why this major problem is basically hiding right in plain sight.
So, turtles have this wild biological quirk. They've got delayed sexual maturity paired with massive adult survival rates. Meaning, some of these adults can just persist for decades, happily swimming around and basking, even if their reproduction completely failed like 20 years ago. And since juveniles are notoriously difficult to detect, traditional capture models just end up dominated by these lingering adults. If we wait around for the adult numbers to finally drop, we've totally missed our window to save the population. We desperately need a leading indicator.
Which brings us to Section 2, the replacement ratio benchmark. This is the core mathematical and biological theory powering the TurtleStatus tool.
So, what exactly are we looking for here? Well, we aren't just blindly throwing together every tiny, hard-to-find hatchling. Instead, we're targeting a very specific biological window called the replacement stage. Basically, these are near-mature turtles, those newly recruiting breeders that are still behaviorally and detectably distinct from established adults, at least for a specific number of years. What we want to see is a reliable, steady pipeline to future adults.
And here is the really brilliant part of how this framework operates. The biological expectation, meaning exactly how many replacement stage turtles should exist per adult, is calculated completely independent of the dataset you upload. It relies purely on known life history traits, things like adult survival and the duration of that observable stage. So your uploaded data never actually alters this baseline. It simply tells the tool how your specific local population stacks up against it.
Okay, let's move from theory over to practice in Section 3, preparing observation data. Because, as we all know, to get good insights, you absolutely have to get your inputs right.
TurtleStatus can actually process data from 3 different pathways: capture records, basking-camera observations, or nesting surveys. But no matter which pathway you're using, your dataset has to follow a minimum schema. You absolutely must map a survey year, the count of established adults, and a biologically validated replacement stage. And it's strongly recommended that you also include your site, your method, like a specific trap type, for example, and your effort, such as the number of trap nights.
But hey, I have to give you a massive warning right here. Beware of stage mismatch. You've got to harmonize your data with the biology before you upload anything. Do not just take every single tiny hatchling and juvenile in your spreadsheet and lazily rename them all subadult. The duration of the observable stage in the tool literally must perfectly match the biological window you use to define those animals out in the field.
All right, moving on to Section 4, the 4-step workflow. Let's look at how the software actually works when you open it up in your browser.
The good news is, when you log in, you aren't going to get lost in some crazy maze of complex menus. You'll hit a very streamlined, 4-step process that's designed to keep your analysis totally focused and completely logical.
Let's step right through it. In Step 1, you search for your species and select your monitoring pathway. Then, in Step 2, you just drop your CSV or Excel file right into the browser and confirm those column mappings we were just talking about. Now, Step 3 is critical. This is where you review your evidence quality and tweak any transparent biological assumptions. Like, if you know adult survival is way lower in your specific wetland because of roadkill, you'd adjust that assumption right here. And finally, Step 4 is where you sit back and read the actual assessment outputs.
So you've hit run. What is the software actually trying to tell you? Let's decode that in Section 5, interpreting linked evidence.
Probably the most common mistake people make here is looking for just one single magic number to give them a definitive answer. You just can't do that.
You really have to read the assessment as a set of linked signals. A single percentage is never a standalone verdict. You have to look at the replacement signal, combine it with the direction through time, the strength of your evidence, and the modeled outlook to truly understand what's actually happening out there in the water.
Let's see how those linked signals play out in practice. Imagine a fictional example where you have a species-specific baseline. You plot your observed ratio of the pipeline against it. Now, you might notice your observed ratio is technically sitting above expectation, which sounds awesome at first glance, right? But then you look at the trend, and it's been steadily declining over an 8-year period. The pipeline is deteriorating. This is exactly what an early warning signal looks like. It's essentially a prompt for you to maintain strict, standardized monitoring before things totally cross the benchmark and fall off a cliff.
But that begs the question, how much data do you actually need to generate a reliable trend like that? Well, the technical manuscript ran some pretty extensive Monte Carlo simulations, and the magic number you're going to want to remember is roughly 200. You need about 200 independent, classified turtles per year to have a really high probability of flagging a 60% decline in the ratio. If your samples are too small, the tool is just going to give you wide, highly uncertain intervals. Which naturally leads to an incredibly important rule, especially if you're using camera traps. Having 20 pictures of the exact same turtle basking on a log over the course of 5 minutes does not equal 20 demographic observations. That is just turtle paparazzi. You absolutely must deduplicate your individuals or use strict independent observation windows. Otherwise, you're just artificially inflating your sample size and totally ruining the analysis.
As we start to wrap up, we really need to establish some firm boundaries. In Section 6, Essential Limitations and Scope.
TurtleStatus is a highly specialized tool, so we need to be crystal clear about what it is not. You should absolutely use it to compare an observed ratio with a life history benchmark to screen for early warnings. But do not use it to estimate the absolute abundance of your population. It is not out there counting total turtles. And do not use it to replace a formal, fitted population viability analysis when you're making regulatory decisions. Think of it strictly as a data triage framework.
In fact, to prevent any kind of misinterpretation, the creators actually provide exact template language you should use when publishing your reports. It explicitly states that TurtleStatus was used strictly as a screening framework, not an abundance estimator, and it notes that any red alerts were manually audited for changes in effort, site, or method before anyone jumped to a biological conclusion. Seriously, use this exact language to protect the integrity of your findings.
So, I'm going to leave you with this final, provocative thought. If your adult turtles look absolutely fine basking on a log today, are you absolutely sure their replacements are already in the pipeline? Because as we've just learned, the demographic illusion can hide a total collapse until it's entirely too late to fix it. I highly recommend you grab your datasets, map out your columns, and use TurtleStatus to find out the real truth about your populations. Thanks for joining me on this explainer, and happy learning.